This is Math 2265. This is the lecture scheduled for April 5, although I'm making it available as early as March 26 if you wanted to get a head start or just not worry about it over the break, get it done early or something over the break if you're not really doing much. Get you something to fill in the gap that might be there, and it's relatively easy material as well. I've decided to go back and do the central limit theorem. It's a very important theorem. I gave you the main gist of it, essentially trading in sigma for sigma over square root of n. That's kind of the heart of the matter. There's a lot more to it than that. We'll see if we can explore more problems involving that, including a couple of sections from the new book and even a flashback to the old book, which I'm not going to be using as much. But in this case, I did find a couple of very good problems that I can borrow, so I will do that. Even I'm going to get a glimpse of the 1101 book that I'm using and 4 of my other classes, because they had actually a very nice visual explanation of the central limit theorem. And that's what this is about. We're looking at chapter 7 of the new book, the central limit theorem. So we're actually going back a chapter, kind of different, but this class has been rather different. Being at the last minute, I got the book and realized that later on it was much, much harder than I planned for. So we are stepping into the OpenStax book, which is free. They talk about the central limit theorem. It's one of the most powerful and useful tools and ideas in all statistics. And they mentioned there's a couple of alternative forms. I'm not too worried about that. Both alternatives concerned with drawing finite samples size n, typically 30 or more, from a population with a known mean and a known standard deviation. And it says we collect samples of size n with a large enough n, say 30 or more, calculate each sample's mean, and create a histogram of those means, then that resulting histogram would tend to be an approximately normal bell shape, even if it didn't start that way. And the second one says if we again collect samples of size n that are large enough, calculate the sum of each sample, and the resulting histogram would again tend to be that. But we're not going to be focusing on sums. This book is, for some reason, doing that. And I've never really seen a book that did that, so I'm going to ignore those examples, basically. And this collaborative exercise, which is good, I think is best explained by looking at actually the 1101 book, which I find a bit ironic. What they're doing here in this explanation is they're rolling a die, 6-sided die, 500 times. And as you probably know, the chance of rolling a 1 on a single roll of a single 6-sided die is 1 chance out of 6. A 2 is 1 chance out of 6. A 3 is the same all the way to 6. About 17% of the time, 16.7% of the time. So when you roll the die 500 times, all the values look like they're about the same. Because of random chance, there are some minor differences, like the 4 is a little low and the 6 is a little high, but they're all roughly the same. If we get to chi-square goodness of fit tests, which I would like to do, I typically do that in semester statistics classes, then we could actually test this and verify that even though it doesn't look perfect, that it's going to be close enough. Now, if somehow the 4s were like half what the 6s were, then that would violate some principles, and the chi-square test would say, nope, not close enough. It's called a goodness of fit test. We may or may not have time for that, I don't know. But silly of them, they put a bell curve over this, I guess to show you how really it's not a very good fit right now, because it's starting at a uniform distribution. We did talk briefly about that, and we'll have a little bit more to say about that in a few minutes. Well, then we average 2 rolls. Now, when you roll, like in a game of Monopoly or craps or whatever, you always look at the sum of the 2 rolls, right? 1 plus 1 is 2, or 6 plus 6 is 12. But now we're going to look at the average. The idea is to look at the sample means when it comes to the central limit theorem. So even though there's only 2 rolls, it's surprising how the sample means already are starting to form a vaguely like a bell curve. Now, the bell curve they fit to it is much lower for some reason. The scale is a bit off. And also, speaking of scale on the x-axis, why couldn't they have just picked 1, 2, 3, 4, 5, and 6? Oh no, they had to get fancy, picking a value that can't even happen, 0.8, value can't even happen, 6.4. But still, the numbers are landing about where we thought they would. And since the average roll in a single die is 3.5, the 3.5, which is about here, does seem to have already the peak of those 500 pairs of rolls. So yeah, it's already starting to show up. And then we could even blow it up a little further, get a kind of a zoom look at this one, and average of 5 rolls down here as we spread it out along this strange little axis they have. It's already starting to look bell-shaped. It is not perfect, and even after 10 rolls, the second graph, it's still not perfect, but it's starting to get a little tighter, a little squeezed in. Another property of the central limit theorem is n grows, it gets to be a tighter, more compact curve with a smaller overall standard deviation. And with 30 rolls, you can see it's squeezing towards the middle even better, although there's a bit of a hole at the top. But hey, that's what we mean by approximately normal. It would definitely satisfy any goodness of fit test as far as being approximately normal, depending on your standards. Anybody's normal standards would say, yes, that's approximately normal. It's getting better and better. You get up to 50 or 100 rolls. I have other books that show how it's even a better fit than that in most cases. This is just based on simulation. Okay, so let's go back to the main book and collaborative exercise. I basically just did that. So let's zoom into 7.1 and take a close look at that and take a look. We're going to be not even covering 7.2. We're not going to do sums at all. They, for some reason, think that that's important. I've never really seen a statistics book that made a big deal out of that. Usually it's ignored. But I don't know. Maybe it's just a different audience. Like the other book is primarily for engineers. This book, I'm not sure what it's for, but it's free and it's pretty good for the money, I'll tell you that. Well, anyway, x is a typical random variable that with a distribution. Might not even know what it is. Could be pretty much anything. We don't want to see a Cauchy distribution, but besides that, I always joke about that one. I think this Russian guy in Siberia had nothing else to do but invent a distribution that just caused headaches for mathematicians, and he certainly did that. Well, anyway, the mean, of course, mu of x is just like the mu, no change, but the standard deviation, which is also known as sigma x divided by square root of n, and usually this x is a subscript. That looks like a mistake. Down here in the more typical formula, that is a sub x, sigma sub x. So I've already zoomed in pretty far, but that's basically just changing the z formula slightly. The mu is really the same. Oh, x is turned into x bar. So we're looking at the sample means distribution. So not individual x's, but overall x bars. And then we make a change down below and say it's not just sigma, it's sigma divided by square root of n. And that's what the central limit, that's the heart of the central limit theorem. So they say that. You can certainly read this. I can skim through this here for you. And all these sample means tends to be normally distributed, even if it didn't come from normally distributed situations. Now, if you have a really oddball distribution, you just have to get bigger and bigger samples. Like maybe instead of 30, you might need 1,000 for some other weird distribution. But after a while, at some point, it would still become approximately normal, which is an amazing fact, considering you can start with virtually any distribution and it'll become normal if you take enough means. And as I used the analogy in the other class, say you have 30 pollsters going out and getting exit polls or polls that aren't even exit polls for election day, and so they get different distributions of the vote total that they predict for candidate A, or maybe even candidate B, or maybe both. And so those estimates would tend to cluster around a bell curve, even if the data didn't come from that. Okay, so anyway, you can repeatedly draw the samples. I'm not going to read through all of this, but the standard deviation is the square root of variance. So basically, they talk a little bit about how that's done. We wind up dividing with the square root of n, because the variance, in case we cared, would be sigma squared over n. But I've never been a fan of variance. Sometimes I could throw it in for a point or something like that, but I just don't really use it. Standard deviation is far more appropriate. Now, this book was going to lean heavily towards the use of the TI calculator, and I'm going to have to start doing these recorded ones on Zoom so I can actually write on the page, because right now I really don't have a working tool that will write on the page. So what I'm going to have to do, like I did in my other class, is to just vocalize and point with the pointer what I'm going to try to do. And I'll try to at least a few times work out the z-scores for you, because I think they've got a life of their own. They're also important on their own. And you don't even have to use a table with them. You could still use your calculator with them. But I've always found some people, since we don't exactly require a TI or equivalent, and if you're one of those that doesn't happen to have one, and remember PC is really illegal on the test, we could go ahead and just ask you to use the z-score and then use the table. So the tables are available, and so go ahead and use them. And there's slight round-off errors, but we do not care about them. Well, anyway, if you're using the TI, it would be normal CDF, lower value, upper value, or min-max, mean, and then the standard deviation, which in this case will be sigma over square root of n. We're looking at the sample means. So here's a good example here. The mean is 90 from this unknown distribution. Standard deviation is 15. And samples of size 25, a nice perfect square, are drawn randomly from the distribution. So that's a very nice thing. And what we can do is to show the solution. And so what they'll do is they'll say mu is 90, sigma is 15, and it's 25, and so we divide this out, 15 over the square root of 25, because we're using the sample means now. Notice the mean does not change at all. It's one of the easiest things we do in both my classes. 15 over 5, square root of 25, 15 over 5 is 3. So now we've shrunk this down from 15 all the way down to 3. That's the narrowing in that we saw with a slightly larger sample size. So this x bar between 85 and 92 works out to be the same thing as z being between minus 1.67 and positive 0.67. So I wish I could write that down. A little bit frustrating. I'll check into the Zoom, but switching the screen seems to be an issue with me, so I will investigate that further next time. But it seems like the majority of you have a TI or equivalent. Please tell me what you did briefly. I would really appreciate that, unless it's a multiple choice question, and there'll be a few of those. But anyway, we want you to at least substantiate what you did. And so anyway, I find those particular values, and if I use the table, which is the way I taught for many years and still do sometimes, you get 0.9525 for the larger number. This is replaced by 1.67 on the z-scale, and actually 0.67, I'm sorry, then a minus 1.67 over here, drawn more or less to scale. When you give me a sketch, which I will ask for sometimes, try to do it roughly to scale. I'm not going to worry about it like I do a box plot, but still, make sure 85 is to the left of the mean. You should always indicate the mean, or z equals 0. Anyway, those cumulative values that you subtract are 0.9525 minus 0.2514. So that gives you about 70%, 0.7011, and you'll notice that the TI is giving you a more accurate answer. This is one of those cases where because of the rounding on z, we actually get slightly different probabilities. So that is a weakness of the z notation, but you would get full credit if that's what you're using and it's obvious by your work that you're using it. Don't just throw me a number with nothing to go with it. I don't think anybody in this class will do that, whereas in my other classes perhaps I would get some of that. So 70.11% versus 60.97, that's off by 0.0014. That's not terribly bad, but more likely you're going to get errors of 0.0001 or even no error at all to 4 decimal places. That's a little bit more common. Okay, so this is all you'd have to type in. Makes it very easy with the TI. I just hope it doesn't remove any thinking that you use to do it. And 85 min, 92 max, 90 mean, and 3. You can just type in a 3. Because this one works out so nicely, I would just do that. But in many cases, if it's the square root of 27 or something, you just type in 15/SQRT or whatever your function is, and then the number, and make sure it gets calculated. So a value that's 2 standard deviations above the mean is found from another formula. By reworking the main z formula, you get an equivalent formula. That will be x equals mu plus z sigma. I can't write that down. So x would equal mu, there it is. So x value is mu 90, and then plus z, which in this case is exactly 2. Notice they said 2 standard deviations. That's a rare problem. So z is exactly 2, and then comes your sigma. This time, of course, that sigma is sigma over square root of n. So then you see that you get your 3 there. 2 times 3 is 6, and 90 plus 6 is 96. And I like this formula because it shows you what's going on. You don't have to do a sketch necessarily, but it visually shows you what you're going to do, because you start with the mean. That's your center point. And if z is negative, you go below it. If z is positive, you go above it. So it's a functional use of the z. I think this is quite important to see what's going on versus just blindly typing numbers in and getting a number in and saying, oh, here's your number, boss. And the boss looks at you and says, you're fired, because it doesn't make any sense at all. Not good to have no kind of sense of direction at all, which I'm afraid I've seen a few people in my lifetime have that, even on a business type of situation. And that's just a very sad experience to see. Hope it doesn't happen to anybody here in this class. Far more important than getting just a grade. I've said that over and over again. Standard error of the mean, of course, was 3. We already said that. And the standard error of the mean is a description of how far, on average, that the sample mean will be from the population mean in repeated simple random samples of size n. So it's just a typical dispersion number. And we had 2 of those on the high side to get a value of 96. And in my formula again, once again, you can say that's equal to x equals mu plus z sigma. So we've got the triads, so you can try those if you like. Let's see if 7.2 is worth doing. Anything that says sum I am skipping over, so I'm not going to even look at those. But this one is a nice one. X is the time in hours it takes to play one soccer match. Soccer is extremely regular, unless they have a shootout or overtime. They play 90 minutes plus halftime. That's the way it is. As compared to, say, baseball, that can be anywhere from 2 hours to 6 hours, depending on extra innings. Anyway, the sample mean time in hours would be what we need to find. They'd like to see probably the sample mean is between 1.8 hours and 2.3 hours. Okay, so the data is mu is 2, sigma is 0.5, but because we have 50 games that we've measured time-wise, we can actually shrink that standard deviation down significantly. That value is now 0.0707, very tiny number. That means that this is a much wider graph than it seems. If your standard deviation is 0.07, and we're changing it to go like, here's a minus 0.20 and here's a 0.30 away from the mean on either side, then it's going to be much bigger. You can see the answer. It's virtually 100%. So soccer games are very predictable. TV stations love that. And not so much games that go into overtime or 15-inning games or 18-inning games. But anyway, you do have that kind of a thing. And the CDF, normal CDF, will give that to you directly. Or you can convert to Z if you have no other option. And if you do, you will find that the first Z would be 1.8 data value minus 2 the mean. Divide by your 0.0707. That z-score is negative 2.83. It's barely on the table. The high side z-score is even worse because it's off by 3/10. 3/10, 2.3 minus 2, divided by 0.0707, this number here, which they did not write down, that's a z-score of 4.24. That's off the scale. We'll just go ahead and call that a 1. Sometimes people say all 9s. Either way, when you subtract it out, this number actually matches exactly what the calculator would give you. So I'd say close to the majority of the time, around 50% of the time, the z-score table will give you exactly the same value as the calculator, and then sometimes it's off by a very slight amount. What we just saw earlier was a bit rare, but that's because of the heavy rounding on the z-score in that particular case. It actually made a difference. Okay, and there's a try it that you can do, and of course there's not much explanation I can give with the calculator. You just type in the low number, the high number, the mean, and the standard deviation, and the calculator tells you the answer. So I hope you have some kind of perspective as to what's going on. That's why we'll ask for graphs or sketches on this later on. So yeah, here's the idea for the percentiles inverse norm, which is frankly a windfall for the calculator. It really does help if you have it for you. And area to the left has to be the cumulative area, no matter what it says. You've got to make it so. And then the mean and then standard deviation, that's just your standard deviation divided by square root of n. So here's this example here, example 7.3. And let's see if I turn to my notes here. I will not be looking, well, yeah, I'll be looking at A and B because they're actually pretty easy. So here's a study on the Flurry blog. The mean age of tablet users is 34 years, and then suppose the standard deviation is of 15, but we have a big sample size of 100. What are the mean and standard deviations for the sample mean ages of tablet users? Well, the mean is exactly the same. Don't touch it. It's perfect as it is. However, sigma, 15, is now divided by the square root of 100. 100 is my favorite number because the square root of 100 is 10. Dividing by 10 is a piece of cake. 15 over 10 is 1.5. Your standard deviation for this set is 1.5. What does the distribution look like? Well, of course it's approximately normal. The odds are it started off normal anyway. And that just gives it a head start at becoming normal. You might not need n to be 30 anymore. Sometimes n could be very small if you've already started with a normal distribution, but that's a moot point. They've already given you a big N, so who cares what the distribution was? It actually does not matter because we already have a big N that has us covered. The only times we'd have to be worried, this does not affect us specifically, if you had a small n and a non-normal distribution. Other books have made a big deal out of this. These books are not. Then you'd have to depend on some other fancy distribution that we're not really going to talk about. So for small sizes with unknown distributions, that would be a bit of an issue. Well, anyway, part C, some math here finally, and find the probability the sample mean age is more than 30. Well, 34 is the average, so that's going to be more than half for sure, the reported mean average age of tablet users in this study. So we'd have to get the z-score, and I'll show the solution. And it turns out that z would equal 30, the value, minus the 34, because we're starting off below average and then going to the right. That'll be divided by the 1.5 that we calculated. Negative 4, the difference between 30 and 34, divided by 1.5. A z-value of minus 2.67, table value wouldn't be too helpful here. You'd have to subtract that from 1. The calculator kind of does that for you already. Anyway, your value is 0.9962, which is in total agreement with how the calculator would work as well. Of course, you type in the 30, type in your version of infinity. This one doesn't need the 1. My calculator needs a 1e99. But either way, your calculator works. And then here comes your mean and your standard deviation as previously calculated. And that was such an easy one, you didn't have to type that in there. Now the 95th percentile, that says that only 5% are above you. In other words, the cumulative value of z is 0.9500. That could actually be found from a table, or really from the 90th percentile of the confidence intervals, which we talked about, and that's 1.645. Now they're not using that because they're going straight to the inverse norm command. They're going to say area left, because that's percentiles, perfect for percentiles, 0.95, then the mean, and then the standard deviation, which this time they decided to type in the long-winded way. I guess they didn't edit that very well. That works out to be 36.5. That could also be done with algebra. So for those of you who may be interested, or those of you who do not have the programmable calculator, or are not confident in describing what you did with the programmable calculator, one could use the formula x equals mu plus z sigma. That would be 34 for the mean, plus 1.645, value of z, times the already known 1.5, and that would give you 34 plus 2.5, which is 36.5. And that would be a constructionistic way to go. And once you're confident that you know how to do it, then yes, by all means use your calculator. But if you really don't know what the calculator is doing, that's like playing with fire. Believe me, you don't want to do that. Okay, so let's look at this example here. The mean number of minutes for app engagement is, let's see, yeah, this is a pretty good one. Let's try this one. For app engagement by a tablet user is 8.2 minutes. Suppose the standard deviation is 1 minute. Take a sample of 60. What are the means? Well, the mean is exactly the same, it's 8.2. And then we'd have to take our 1 for the standard deviation, divide by the square root of 60, which is small. Let's show the solution. They're going to work this one out for us. And that's a very small number, 0.13. This allows us to calculate the probabilities of sample means at a particular distance from the mean. Repeated samples of size 60. That's called the standard error of the mean, also known as sigma over square root of n. That's what the standard error is, just another way to say it. 90th percentile, very easy on the calculator. Area left, 90%. Here's the mean. Here's your new standard deviation for x bar, sample means. And you could, of course, use the other formula too if you'd rather do that. You just say that x equals mu plus z sigma. You'd have to look up the z and all that, but here I'm not going to do that for you. So 90% of the average app engagement times for tablet users is less than 8.37 minutes. Notice how close that is to 8.2. This is a very tight standard deviation. There's not much wiggle room. The difference of these two numbers is 0.17 of a minute. That's about a sixth of a minute. That'd be about 10 seconds difference, and you're already in the 90th percentile. But then you're talking about a group of 60 people, so it's not all that surprising if you think about it. Get 60 people to move even 1 second is a lot harder than one person to do that. The motion is multiplied 60-fold, in other words. Now find the probability that the sample mean is between 8 and 8.5 minutes. This straddles the line between the mean. I've drawn a sketch. I wish I could show it to you, but as I try to draw it out for you here, if you can see it, 8.2 would be in the middle, and 8 would be on the left side, and 8.5 would be on the right side. So you're straddling the middle. And then I found the z-scores and I looked them up in the table and verified it on the calculator. If you take, say, 8 minus 8.2 for the z-score and divide by 0.13, the first z-score has already moved over to minus 1.53, and the high z-score is 2.31. And the difference of those two values, which are pretty extreme, one is 0.9896, the other is 0.0630, you would get 0.9266, which is kind of pretty far off this time. That's one of those that didn't really make it very well. So the z approximation can be off by a little bit. There's heavy round-off error at work at that point. Not going to cover 7.2. That's just ridiculous. In fact, I'm going to go over and take a look at, as we cross into 7.3, and what is the topic there? More on the central limit theorem. And in this case, its title is regarding the t-distribution. So here we have to use the t-distribution for some of these. Actually, I apologize, we are not using the t-distribution. This is just more of the same stuff. And here we have worked out examples in terms of z, etc. So the amount of a particular impurity, and this, by the way, if you're looking, this is section 5.4 in the old book that I'm not using too much anymore, but I still will look at it. The homework is coming from the old book. All that's in WebAssign now, but I picked the easiest problems that cut across the board amongst any book. Slight notational differences. I don't think they're much of a problem yet, but if they become an issue, I will send out an announcement about it, such as p hat is the same as p prime, exactly the same. Okay, so this impurity in a batch of a certain chemical product is a random variable. The mean is 4.0 grams, standard deviation 1.5 grams. 50 batches, n is 50, are independently prepared. What's the approximate probability that a sample average amount of impurity x bar is between these two numbers, which by the way are both less than the mean? Okay, n equals 50 is large enough. They like to say that 30 is a criteria, and I agree, for the CLT, central limit theorem, to be applicable. So we have a normal distribution. They've already calculated the new standard deviation, 1.5 over the square root of n. That's really all. The major change is to get that square root of n divided into the sigma on. Shrinking down your standard deviation a lot and driving up those z-scores and widening the probability most likely. Well, anyway, they show the calculation of z. Let's see if I can, well, if I zoom in too much, I can't read the other side. But this is a z value. Don't worry about the phi notation. That just says we're finding the z values, the probabilities. I've not looked these up, but they do look like they would work. From your table, even from your calculator, you can find a particular value that's this number minus the other number for a negative 2.36. This is much further away from the mean. Actually, well, we crossed them, yeah. So this one's further away from the mean. This one's closer to the mean, so it's actually crossed. And when you subtract those two values out, you would get about 16.5%. Now, if we change it up and consider randomly selecting 100 batches, now they're looking at the total impurity, the mean and standard deviation are, well, they go through all these other formulas that we're not going to really be needing. I'm not going to be doing sums, but this is what the other book is also doing. And so they just show another z calculation. When you have, say, less than 425, it says at most 425. That means less than or equal to, because 425 is the maximum it could be. So in this case, they don't do those adjustments in the same way. I'm not going to go in that direction. Don't worry about it. Just one more example here. X is the number of different people sending text messages during a particular day. Suppose the mean value of X is 7. Excuse me, and the standard deviation is 6. And they have an article one could look up. There's 100 randomly selected students. How likely is it the sample mean number of different people texted exceeds 5? Well, the mean is 7. So we're going to have it just go 5 and up. We're going to grab the entire right half of the distribution. So it's going to be at least 50%. In fact, cutting down to the end, it's almost 100%. So yeah, it's quite large. But this distribution is discrete, but the theorem is applicable whenever the variable of interest is discrete or continuous. There can be continuity correction applied, and I have an example of that if we have time, from the normal approximation of the binomial, which we saw back in chapter 4 on the old book. Although the fact that the standard deviation of this variable is quite large relative to the mean value suggests that there's a skew, a positive skew, the large sample size implies that x bar does have a normal distribution. So we've got 100. That really helps. So anyway, that difference of 5 minus 7, negative 2 below the mean, is divided by the standard deviation, which they've already handed to us. It's 0.6. Minus 2 over 0.6 is a negative 3.33, which is barely on the table. And one could subtract that out because we are going greater than that. Our sketch this time would have almost the entire curve. It would just lop off a tiny bit of that left tail at negative 3.33. Notice, because it's a greater than calculation, you would have to subtract it from 1. And that gives us a very large probability. So it's almost certain that the sample mean would be 5 or more. If you've already seen that it's 7 and you're getting a big sample, 5's already fallen a little far from the tree, so to speak. And so that's going to be just about impossible to miss. So anyway, that's provides insight. This theorem provides insight as to why many RVs have distributions that are approximately normal. Measurement error nearly always turns into errors that are normal or bell-shaped. And they do say, once again, that n should be greater than 30. But there are other cases, I think of subdistributions, where 40 or 50 isn't even good enough. But those are rare, fortunately. So most common distributions, you might get by with less than 30. They do have a picture here based on a simulation. I'll let you skim through that if you'd like. They also have from another example here, sample mean amount purchased when n is 15. Looks like the sample here was around a 26 or 27. Looks like that's becoming quite close to normal here. And this is the sample mean distribution when the amount purchased from n equals 15. And that wasn't even 30, and it's already bell-shaped. So sometimes you get a bell-shaped even when you don't expect it. Okay, so let's go over to a little bit of 7.3 in the time we have remaining. I'm not planning on covering the central limit theorem for sums. It just is not important to us. I've never really seen that made a big deal of, and I just don't want to open that door because I'd rather just stay with the main message. Okay, when to use the central limit theorem? If you're being asked to use the probability, as we go back to the regular new book, OpenStax, use the CLT for the mean. We're not going to do the sums. So anyway, if you're just looking for an individual value, there's no need to use the central limit theorem. Why? Because n is 1, and sigma over the square root of 1 is just sigma. It's a bit of a waste of time. The individual and the sample are the same, and the mean of the individual is just the individual. So there's no real point in doing that. Although it wouldn't hurt, I guess, just make sure n is equal to 1. It just looks a little strange. As n gets larger and larger, the sample means become more normal and also more squeezed, as we saw in the diagram earlier where the scale showed how the curve was getting closer and closer to the center because of a smaller standard deviation based on a large n. So sample mean must be getting closer to mu. Has to be with bigger samples. And mu is the value of the sample means approaching as n gets larger. And it has to do with the law of large numbers. So here we have example 7.8. I guess I can work through some of this. It does involve the uniform distribution, which we've seen. There's a calculation here that we've not done and we will not worry about at all. But what's the probability that the mean stress score, because there's a study involving stress amongst students on a college campus, and follows a uniform distribution with low as 1 and high as 5, sample of 75 students. We'd like to find the probability that it's less than 2. Okay, well, the mean kind of easy. Just take the average of 1 and 5. After all, it is a straight-up uniform distribution. However, the standard deviation is something we've not seen. You're not responsible. Just pretend as if it was given to be 1.15. That's it. So that's all I have to say. You're not going to be needing that formula. I'm never going to ask for it, although they do use a capital U for uniform. But point is, we've got the sample of 75. So to get the real standard error, we take the 1.15 and divide by the square root of 75. That's a very small number. It's 0.133, very similar to what we just saw. Find the probability that x bar is less than 2. They're heavily into the calculator use, but at least they have a sketch here, which is nice. Turns out that when you divide that out, you get a z-score of, well, 2, the value, minus 3, the mean, divided by what we just said, 0.133, this value here. That's a z-value of negative 7.52, way off the scale, very, very small. Your calculator would tell you exactly how small. I don't really care. You can tell me if you like, but it's virtually zero. Anything that's below 0.00004 decimals rounded, when it just shows a zero, maybe just say approximately zero. That's good enough. And so is the calculator. Although you could probably stretch down and see 10 to the minus 34th or something like that. But of course they put the minimum value, maximum value, mean value, and then standard error, sigma, the new sigma over square root of n. And the smallest stress score is 1, highest score is 5, so 3 being the average. To get less than 2 would be pretty hard out of 75 people. In fact, it's not going to happen. Okay, what's the 90th percentile? The one that separates the bottom 90 from the upper 10. Nice picture here. I like the pictures. So we'd like to find k, where this probability of x less than k is 90%. There's a formula that they're going to mention pretty soon. I'll just give it to you now. By reworking the z formula, where z equals x minus mu over sigma over square root of n, you can then solve for x. It works out to be x equals mu plus z times sigma. Mu plus z times sigma. And that's what they're going to use here. At least that's what I'm going to use. I'm going to say that x would equal the mean, 3, and then plus z. Well, we look up the z for the 90th percentile. That number is 1.28. And that'll be multiplied by the sigma, which we found was 0.133. That gives you an extra number of 0.17, or just 0.2 for short, as they rounded to the nearest tenth. And you add the 3 in that number. It's only 3.2. Very small movement because of the large sample sizes. Gets you already to the 90th percentile. We already saw something just like that. So 90% of all means of 75 stress scores are at most 3.2. And 10% are at least 3.2. So there's still 10% to go that are above that threshold. Okay, so for the next ones, we are looking at the sum of the stress scores. I'm not interested in those. Let's please skip anything that says sum on it. Just not interested. Also, example 7.9 depended on the exponential distribution, which we did cover, but I elect not to worry about that here. We've got bigger fish to fry right now, so I'm not going to go there, but you feel free to skim through that. I will not give you any problems based on that. But 7.10 and 7.11 are mostly pretty good problems, so I thought I would at least talk about them for a little while. Not a pleasant topic. Statistics can be fun topics from like free throws or batting average, or it can be something about how many times somebody's been sexually assaulted. And in the U.S., apparently that happens every 2 minutes, although I dare say with COVID it's probably come down, ironically. But now everything's opening up. Unfortunately, stuff like this will happen more and more often, I'm afraid. Well, anyway, according to basic statistics over the past few years, we've got standard deviation is 0.5, sample size is 100, and we have a mean of 2. So it's going to be per the minutes, and that's how they're going to measure it. And the median here is the same as the mean. 50th percentile is sitting right on the mean for now. In fact, in theory, the bell curve says the mean and the median, even the mode, are all the same. So here's a case where we can actually use that, a rare case. So don't worry about that one. Now with 25th percentile, we'll show the solution and show you what they have to say about it. Mean is 2. Standard deviation has been changed from 0.5 to dividing by the square root of 100. That is dividing by 10. Now the standard deviation is quite tiny, 0.05. Pretty big sample, shrinks the standard deviation. And the inverse norm command, which is of course the easiest way to go. Just tell me what you did. I don't think that's asking much. I'm always very surprised by some of the students that just don't want to tell me what they did. And that's like, not being prepared. And the whole idea is to prepare you for stuff. I know the answer. You probably know the answer too. Just write it down. Okay, anyway, I'm always speaking to a few people that I've spent with, and there's always 5 or 6 in every class that just don't want to do it, even though they can. So here's the percentile. This is the 25th percentile, the bottom fourth, where Q1 lives, in fact, from the box plot. There's the mean. Oh, there's actually the maximum, sorry. I'm sorry, that's the mean. There we go, the mean, and then the new standard deviation. That gives us 1.97. The formula, by the way, wouldn't be very hard to do. The percentile for z here would be, for the 25th percentile, is minus 0.67. So your x value would start at the mean with 2, subtract the z 0.67, and times the standard error, 0.05. Doesn't move the needle much, moves it about 0.03. 0.03 to the negative side from the 2, 1.97. 0.03 to the positive side, 2.03. Why is that? 75th percentile is totally symmetric with the 25th percentile. Virtually the same problem, except now z is a positive 0.67 due to the symmetry of the bell curve. What about, let's see, don't care about the sums, not going to do the sums at all. That is not what I'm interested in. And let's see, B is the sum, so I'm not going to do B. Let's take a look at C, though. So C asked us for the probability that an assault occurs on the average between 1.75 and 1.85 minutes. And so the calculator makes it look very easy. Minimum, maximum, mean, and standard error, standard deviation with the square root of n involved. And that's a very small percentage. We're taking a razor-thin slice of this particular curve. I wish I could show it to you. But because the standard deviation is so tiny, we just haven't found very much left over there. This is on the far left side of the curve, even though it doesn't look like it. Because we had 100 people in our survey, it's so centralized that if we try to move it away from the center, it just isn't going to be there anymore, which is why it's very close to zero. And it would be a simple matter to figure that out with the x equals z sigma plus mu formula. In fact, they do that over here in part D. They finally show that formula. Find the value that is exactly 2 standard deviations above the sample mean. So they're saying use the z-score equation, x bar minus mu over sigma over square root of n. Solve it for x, like I've been doing. X is equal to z sigma plus mu. I like to say mu plus z sigma, same formula. Well, the 2 is the standard deviations. They said 2 standard deviations, that's your z. We've already found the 0.05 for sigma, and the mean, ironically, is also 2. Not too confusing, I hope. But that only moves the needle 0.1 of a unit, plus the 2 is 2.1. And that's already 2 standard deviations above the sample mean. Those standard deviations are very tiny. They're like nickels, and then we moved it over to get a dime. 2 nickels make a dime, $2.10 instead of $2. Well, the IQR is kind of hearkening back to the box plot, but it did say sum. Not interested in sums. Not going to give you any of those. Not accustomed to that. Not going to start now. Too much else to talk about. Let's then look at example 711, parts of it, ones that don't have sums in them. So I'll be looking at A, B, and E to kind of wind it up for today. And then you can either remember fondly your break that you had earlier, or look forward to your break like currently I am doing now, although I don't really have completely a break. I do have tutoring. I do have to write tests and do other things, so I'm not going to be really going very far. The study was done about violence against prostitutes, another interesting topic, I guess, and then the symptoms of the post-traumatic stress they developed. Age range of these people were from 14 to 61, but the mean 30.9 years, standard deviation of 9 years. Somebody had to find these things out, I guess. And in a sample of 25, well, okay, that's not so much using the central limit theorem, but I guess as some books say 25 is enough. That's what this book is assuming. Let's go ahead and take a look at that. What's the probability that the mean age of the prostitutes is less than 35? I'd have to say it's pretty big, because it's pretty far away from 30.9. And we're talking about less than that. Wish I could show you the sketch, but if the sketch has about 30.9 in the middle, and then 35 is way over here, we're going to harken back to the entire rest of the curve. It's everything but that little right tail slice. The little slice of the right tail, there's big, over 35, because some of them are actually much older. Doesn't add up to much, but by using the normal CDF command, the answer becomes very easy to get. There's your version of minus infinity, whatever it may be on your calculator. Maybe you don't need a 1 in front of the minus sign or back of the minus sign. Stop at 35, put in the mean of 30.9 and your standard deviation of 1.8. And how did we get the 1.8? Well, that's 9 years divided by the square root of 25. Square root of 25 is 5. That's nice. 9 over 5 is 1.8. So that's where they got it. And typing that in, you see it's just about 99% of the time. Yeah, that's not very much. But then, well, that's quite a lot, I'm starting to say. And then the z, by the way, would be 35 minus 30.9, a gap of 4.1 years. and that'll be divided by the 1.8 that we just saw here, giving a z-score of 2.28. We're going to go less than 2.28. Even the table will tell you that it's 0.9887, very close to the calculator answer, which of course is more accurate. For part B, is it likely that the mean age of this group could be more than 50 years? No, it's not. It's so obvious. The mean is around 31. We're talking 50 or more? Come on. So anyway, you type in the numbers. The difference now is the minimum is 50, and we don't have a maximum, although one could argue you could put a 61 in, but that makes it slightly less accurate, believe it or not. And keep the 30.9 and the 1.8. It is almost impossible for the group's average age to be more than 50, but it's still possible, definitely possible, for an individual to be greater than 50, and they even said that it would be. So looking at the z-score, though, out of curiosity, when you put in 50 minus the mean of 30.9 following the formula and dividing by 1.8, that z-score is supposed to be greater than 10.61? Give me a break. That is virtually impossible. So just back up for that. And let's look at E, because the others involve sums. Not interested in sums, as I've said. Find the 95th percentile of the sample mean age of 65 of these prostitutes. That's the sample size. Well, by the calculator, it's the inverse norm situation. You type in your 95 cumulative probability facing left, and then your mean of 30.9. But now notice how the standard error has changed. We have a different sample now, 65. And the 9 that was given earlier, over here, divided by square root of 65, which is pretty much 8, yields a value rounded to only one decimal. I would have used more than one decimal, of 1.1. 1.1. So anyway, that's how that goes, and they indicate that when that all comes in, it's kind of a mystery how the calculator does it, which I do not find to be a plus, by the way, and that's going to be 32.7. That's amongst the oldest of them. 95% of them of the prostitutes in the sample of 65 are younger than 32.7. Only 5% would be older. And by the way, the X formula, the transformed Z formula, talks about using your mu. X starts with mu, 30.9, and it adds a value for the 95th percentile. That Z value, as we've seen already, is 1.645, equivalent to a 90 percentile, by the way, a 90% confidence interval, I'm trying to say. And that's divided by multiplied by the standard error, which we'd already found to be 1.1. 9 over square root of 65, and I've already double-checked that on the calculator. We find that adds in 1.8 more years for a total of exactly 32.7 to the nearest tenth of a year, which is pretty much a month. And so that verifies that and kind of lets you see what's going on a little bit. The normal approximation of the binomial, I have time for one of these. We did actually cover this. It was back in the old book, section 4.3. So here's a little bit of reinforcement with it. It still can be useful for very large numbers. They're saying in all the books that, technology circumvents that, but I've noticed my TI-83 doesn't cover several large numbers. Maybe the newer ones do. I'd say they probably do. Let's take a look at one or two of these, depending how time goes. Okay, they remember that the mean for this, for the binomial situation, is n times p, standard deviation square root of npq. And of course, q is 1 minus p, but let's not drag the extra baggage. Not like carrying empty baggage with you everywhere you go. It's just no fun. But anyway, we have in a K-12 school district, kindergarten to 12th grade, 53% of the population favor a charter school for these grades here. Simple random sample of 300 is surveyed. Find the probability that at least 150 favor the charter school. So let's see here. X is the number that favor the school. And X is binomial, but N is 300 and P is 0.53 as stated earlier. NP is certainly greater than 5, and it lets us go ahead and use the normal approximation, NQ, same way, because it's pretty close to 50-50. They're both way over the 5. So the formula is here, the N, or mu equals N times P, which happens to be 159. That's 53% of the 300, be exactly 159 people. And standard deviation, which I will not show you, square root of 300 for N, P is 0.53, Q is 0.47, and that does give you an 8.6447. Suddenly they've got 4 decimals of accuracy. It's like inconsistent. The random variable for the normal distribution is then normal with a mean of 159, standard deviation of about 8.6. And so here we would include the 150 because it says 150 or more. And that means for the approximation, you actually have to bend back half a unit. Pretend it's a block, a histogram block that goes back half a unit, just like a Riemann sum in calculus. Same idea. So then you could use your calculator by saying, here's your minimum with the adjustment, continuity correction, and this time they're using 10 exponential notation 99 or E99, 1E99, whatever it is that you have an infinity for. Here's your 159, and then a little extra accuracy for the standard deviation. And it does give us 0.8641. You could also use the z-score, and that value would be 149.5 as found before, minus the 159, the mean, and then divided by 8.6447. That yields a z-value, a moderate z-value of minus 1.10, from which you'll go greater than that. If you're using the table, you would have to subtract the value from 1. So minus 0.1357 yields a 0.8643, very close to 0.8641. Not exactly the same, but not very far away. Now, one that the z-score misses a little bit is at most 160. So this is a left-facing curve that I would like to show you during the live lectures. I'll be able to do that more often. So we include the 160. At most 160 is including the 160. So include the block that ends at 160.5. And so similar things happen. Here we can stop at 0. No need to go into negatives. Just stop at 0 because that's the least number that could ever be in favor of it. And we go to 160.5. And then we put our mean in as calculated before, standard deviation as calculated before, and this is about 57% of the time based on your calculator. And just to show you, if this ever shows up again, more than 155 does not include the 155. So it's greater than, strictly greater than. With a discrete notation, it actually makes a difference. So we then go to the next number, 156, and half a unit back from there, splitting the difference, the numbers that round into 156, another way to put it, we have to use the continuity correction 155.5. And the rest of it's routine. And fewer than 147 means that we do not include 147, which means we take the numbers that round down into the 146, stopping halfway between them, and use the same procedure. Get around 7% of the time. And of course, exactly hitting one number in a continuous distribution would yield a 0. The area of a line is 0. But here, we back up half a unit, we add half a unit, and we then find from the calculator, we don't have to worry about infinities anywhere. Here's the min, here's the max, and the rest of it the same. Works out to be a little less than 1%, but it's not 0 either. So, yeah, it's not necessary to use this so much, but maybe I can find something where some calculators might not work if I pick some very big numbers. Oh, the jury's still out on that one, but it's still nice to know about how this relates to calculus in a vague way, I suppose you could say. And so there is your fill-in lecture on the central limit theorem that was omitted earlier. And I realized, yes, I can actually talk about this, and really I should, because it's a major theorem in statistics. So for me to ignore it would have been kind of an issue. So now we've gotten through chapter 8, and the next topic will be chapter 9. So I expect to start on that when we come back live on April 7. I do plan to get our foot in the door of hypothesis testing, a very important subject. I'm happy to be able to do it a lot sooner than what would have happened with the other book. And so we'll do that for a while and review for the test on April 7 when we're back live. And our test, of course, is on April 12. It'll be from 4 o'clock to 5:15. You'll have a lot less time to submit your PDF this time. I think it's going to be 15 minutes. That should be plenty of time. The vast majority of you did it much sooner than that. Oh, by the way, they misspelled approximation. I've never seen a perfect book yet. But anyway, I guess I could have gotten a proofreading job, but it would have been San Diego. Although I like San Diego, I don't know. It just wouldn't have involved teaching as much as it would have been just regular proofreading. I wasn't into that too much. So anyway, it looks like that's going to do it. Either I hope you enjoyed your break, or you will enjoy your break depending on when you watch this. And but take a break, take some time off, but then get caught up too. And we'll see you back after the break. First one we've ever had, first semester break we've ever had. We'll be back live on the 7th, 4 o'clock, and we'll talk to you later. Bye-bye.